Alright, so here we have a lever or meter stick, and it has a pivot point in the center. If you prefer, you can think of the pivot point as a dot, kind of like how we had in the torque demo in the back of my classroom, where the meter stick can pivot around this point. Okay, so it can move clockwise or counterclockwise. Alright, so it says, does the 30 Newton force provide a positive or negative torque? So if we look at this 30 Newton force, think as if you have this meter stick and you start pulling it down on this left side. Well, it's going to cause it to torque counterclockwise. Okay, so if you take your right hand and cause your fingers to curl in a counterclockwise fashion, you'll notice that you're giving me a thumbs up. Okay, thumbs up means positive. Okay, on the diagram it says calculate the individual torques on the lever. Well, I'll tell you this. The 60 Newton force here is completely parallel. Any force that's parallel to the lever provides no torque. If you're trying to change a tire and you push on the end of the wrench to try to unscrew the bolt, your wrench is not going to move around the bolt. Also, this 120 newtons is pushing or pulling on the pivot. Okay? Since torque is a force times the distance, there's no distance here. Your distance is 0. Therefore, there's no torque. Alright, for this one, we already figured out it was positive, so we can say our torque is our force, which is 30, times our distance, which is 0.1, 0.2, 0.3 meters away. So we can multiply 30 and 0.3, and we get 9 Newton meters. Now, we could technically say it's always the force that's perpendicular to the lever. We'll notice that this force is completely perpendicular to the lever. So the angle there is 90 degrees. So we could say, okay, to figure out how much of our force is in the perpendicular direction, we're going to use sine theta. So we can say sine 90 degrees, but it's all perpendicular. We're going to get the same exact number. So equals 9 Newton meters. Alright, for this 75 Newton force, we need to figure out whether it's positive or negative. Well, if you were to pull up on the right side, that will cause your lever to start moving counterclockwise. Well, if you curl your fingers on your right hand counterclockwise, you'll notice you're giving me a thumbs up. That is a positive torque, where it's equal to force times the distance is from 50 centimeters to 60, so 0.1 meters. And then we have to say sine theta, where our angle is always between the lever and the force, 45 degrees. So we're going to plug in 75 times 0.1 times sine 45. And we get 5.3 Newton meters. Alright, for this last one, if we were to pull down on the right side, it will cause the lever to start moving clockwise. Well, if you were to take your fingers and curl them with your right hand clockwise, you'll notice you're giving me a thumbs down. That means our torque is negative. So negative force, which is 40, times distance, which is 0.1, 0.2, 0.3, 0.4, sine theta, where theta is 30 degrees. So we're going to plug this in. Negative 40 times 0.4 sine 30, and we get negative 8 Newton meters. Okay, so calculate all the individual torques. Check. Alright, calculate the net torque. Well, the net torque is the sum of your torques. It's just all your torques added up. So we are going to take this 9 Newton meters, which is positive, add the 5.3 Newton meters, which is also positive, and then subtract 8 Newton meters for this guy because it's negative. And we add all of those up. So 9 plus 5.3 minus 8, and we get 6.3 Newton meters. Okay, notice that that is a positive torque, so if you give me a thumbs up with your right hand and curl your fingers, you'll notice that they go in a counterclockwise motion. So the lever will begin to move counterclockwise. If you look down at this second problem, it's a little bit different. Our pivot, notice, that it is completely on the left side. Okay, so the distance would be 0.1, 0.2, 0.3, 0.4, and so on and so forth. And it says to calculate this unknown force. So we don't know what this force is equal to. We have to calculate it. Now, since it doesn't say that there is a torque on the lever or that the lever is moving, we're going to assume that it's balanced. So however many Newton meters we have on the top, that's however many we're going to have on the bottom. So we know that torque is a force times the distance, sine theta, but for this guy, it's completely perpendicular, so sine 90 is actually 1, and 1 times force times distance is still just force times distance. So we need to figure out whether this is a positive or negative torque, though. If we were to pull up on this meter stick, it would start moving counterclockwise. If you were to make your fingers curl counterclockwise, it's going to be positive. So we know that it is the force, which is 25, times the distance, which is 0.1, 0.2, 0.3, 0.4. If you were to plug that into your calculator, you'll realize that we have a torque of 10 Newton meters on the top. Well, if the sum of our torques, and there's only 2 of them, is 10 Newton meters plus whatever torque this is, we'll call it torque 2, well, that all has to equal 0, since our net torques are 0 because the lever's not moving, it's balanced. So we know that if the first one, torque 1, was 10, torque 2 needs to be negative 10. So we know negative 10 Newton meters is going to be equal to a force, which is what we're trying to solve, times a distance, sine theta. Okay, so we know, since we have the sine theta, it's telling us it's at 20 degrees, we have that direction, 20 degrees, so we don't need the negative sign. 10 times the force, the distance is 0.1, 0.2, 0.3, 0.4, 0.55. And we have sine 20. So we could just divide 0.55 sine 20 on both sides. And we would solve for our force. 0.55 sine 20 on the right over itself is just going to be 1. Anyway, so 10 divided by 0.55 sine 20 is 53.2 newtons. So this force here is 53.2 newtons.